Now, I'll talk about a translator from FDL to SystemVerilog for FPGA implementation of fuzzy inference. Introduction. Fuzzy inference has been used in a variety of fields because fuzzy inference has an advantage for the problem which is difficult to be modeled for nonlinear problems and can express human knowledge and experience. For software implementation of fuzzy inference, special purpose programming language, special purpose development tools, and fuzzy libraries are usually used for easy implementation. For example, as a special purpose programming language, Electric Industries Association of Japan standardized fuzzy system description language in 1996. A translator FDL2C and FDL library are developed at the same time. Therefore, it became possible to convert FDL to C language for software implementation. On the other hand, FPGA implementation is becoming prevalent in recent years because FPGA implementation usually has the advantage of high speed and low power consumption. About the FPGA implementation of fuzzy inference. This paper showed FPGA implementation of image processing using fuzzy inference for high-resolution video processing in real time. This study showed that the real-time video processing using CPU has limitation in terms of speed, and the higher resolution was difficult. However, there is no hardware development environment for fuzzy inference. Therefore, we have to design with HDL by our hands for FPGA implementation of fuzzy inference, including this paper. But it is not easy for software engineers to design using HDL. Another method for FPGA implementation. There are high-level synthesis tools to generate HDL from a C program. However, C language generated by FDL2C has description of dynamic memory allocation and special purpose library. They are not available on high-level synthesis tools. Consequently, we developed FDL2SV. FDL2SV is a translator from FDL to SystemVerilog for FPGA implementation of fuzzy inference. It became possible to convert FDL to SystemVerilog by FDL2SV. We aim at easy development for high performance of fuzzy inference on FPGA. First, I'll talk about FDL before FDL2SV. FDL is C-like programming language that can express fuzzy set and if-then type fuzzy rules directly. It is composed of the following three parts: definition of fuzzy set, definition of rule base, and main function. Main function is a part calling the rule base, processing of centroid, and processing of I/O. It can be written in C language. Definition of fuzzy set is a part to define fuzzy set used in rule base. This is a sample description. The first line is description of underlying set, including minimum value, maximum value, and number of divisions. The second line and after a description of fuzzy set. Its description of right sides are written using description below. Programmers can define any fuzzy set using this description. This description means a graph on the center of this page. However, it is presupposed to calculate discretely using a number of divisions in FDL. Therefore, internal representation of fuzzy set is shown in the below graph. The last part is definition of rule base. This part defines fuzzy rules using fuzzy set. Words in the first and second parentheses are input and output element respectively. The second line and after are if-then type rules. For each rule, condition part is shown with red and consequent part is shown with blue. I explained about FDL. I'll talk about our work FDLOSV from this page. We developed FDLOSV by C language using Python and Flex. The processing flow of FDLOSV is shown in this slide. Input is pure FDL without pragma or other additional descriptions. First, lexical analysis and syntactic analysis are done, and syntax trees are generated in this process. Next, generating SystemVerilog part generates SystemVerilog using these syntax trees. The quantization bit number can be defined on FDLOSV. This slide shows syntax trees. Left side, rule-based tree is generated using the FDL description of definition of rule-based part. And right side, fuzzy set tree is generated using the FDL description of definition of fuzzy set part. Generating code process is shown from this page. Fuzzy set tree contains both fuzzy set of input size and output size. Our program searches for fuzzy set of input size and generates fuzzification modules as lookup tables using these fuzzy sets first. Next, our program merges each fuzzification lookup tables on the same condition part. Next, our program searches rules that has same consequent part and merges these rules using fuzzy OR operation and generates processing module of consequent part. Lastly, generate a defuzzification module, Centroid. Its processing result becomes the output of this fuzzy inference. Top module of SystemVerilog generated by FDLOSV is shown in this slide. This circuit has only minimum I/O, valid lines and data lines at present. This circuit works as follows. When valid in becomes high, this circuit wakes up and starts processing using values of input. After the end of processing, this circuit outputs the values on output and makes valid out line high. As an evaluation, we made a comparison between software implementation result using C program generated by FDL2C and FPGA implementation result using SystemVerilog generated by FDL2SV. In addition, we also evaluate their circuit area and calculation error. About software implementation, we executed this program on a computer shown in the upper right of this slide. About FPGA implementation, we selected a low-cost FPGA, Xilinx RTX 7, as a target device. A cruise control problem used in this evaluation is shown in this slide. This problem is to control the vehicle to keep its speed constantly, regardless of any road and other circumstances. It has three inputs: E, real speed minus target speed, delta E, variation of speed, and E theta, real throttle position minus throttle position map by target speed, and it has one output, delta theta, operation amount of throttle position. Fuzzy set and rule base used in this evaluation are shown in this slide. The left side of this slide shows fuzzy set. E, delta E, E theta, and delta theta have 4 fuzzy set, 4 fuzzy set, 1 fuzzy set, and 8 fuzzy set, respectively. The right side of this slide shows rule base. This fuzzy inference has these 10 rules. Result of speed and circuit area are shown in this slide. The software generated by FDL2C can transact in about 28.9 microseconds per one inference on average. The other hand, FPGA implemented using FDL2SV can transact 281.6 nanoseconds per one inference. It is about 102 times faster than software. The circuit scale is shown in the table below. It is less even than half of the available resources of target FPGA. Hardware and software implementation results and their difference are shown in this slide. The output value of hardware and software implementations looks almost the same. However, hardware implementation result has errors. Because grades of fuzzy set are quantized as 8-bit and fixed point model operations are used in hardware implementation. The average value of errors of hardware implementation result relative to software implementation result is about 1.89%, and the median value of it is about 0.47%. In addition, its maximum absolute error is about 0.0058. Conclusion: we developed a translator, FDL2SV. It makes hardware implementation of fuzzy inference easily. A circuit generated by FDL2SV is faster than a software generated by FDL2C, and this circuit scale is available on a small FPGA. However, FDL2SV is not available all descriptions of FDL specification at present. They are shown in this table. This is the result that we implemented heavily used and basic descriptions as a priority. In the near future, we will conform to the rest of specification of FDL perfectly. Our future work is summarized as follows. Thank you for your attention.